बिस्मिल्लाहिर्रहमानिर्रहीम। तो आज का जो हमारा टॉपिक है दैट विल बी एनर्जी इन द IR, I can see the vibration spectroscopy, how we calculate the energy, how the energy levels vary, so what is their spacing and so on. And with this we'll also try to include the selection rules and basics. The energy of the molecule in the IR spectroscopy के लिए we derive that energy. We assume that molecule, we assume that the molecule is a simple harmonic oscillator. It's under the limits of simple harmonic oscillator. कैसी molecule होगा एक simple harmonic oscillator when it obeys Hooke's law? So simple harmonic oscillator obeys Hooke's law, that is F is equal to minus kx. ठीक, then energy, potential energy is equal to 1 by 2 kx square. So अगर ऐसे it obeys Hooke's law, it has this potential energy, then it is said to be simple harmonic oscillator. That means during the course of vibration, the bond doesn't undergoes the, it doesn't crosses that limit so that the bond gets broken. Fine. It comes from mean to extreme position, back and forth. So energy we calculate with the help of Schrödinger wave equation. It's very important. Schrödinger wave equation. So energy of a molecule in the IR spectroscopy is calculated with the help of Schrödinger wave equation. That energy is, if we take it directly, EV. Again मैं यहाँ पे focus कर रहा हूँ कि जो मैं यह series prepare कर रहा हूँ for the spectroscopy. It is special when you are dealing with the, the short-term exams, when your examination pattern is very short, your major objective type or one-line type answers, or even two-line answers, that will be very useful. ठीक, क्योंकि हमारा pattern object type है, तो I'm not going deep into the derivations and taking a lot of theory inside. So you can finish maximum things here if you can follow these lectures. So that's given by 1 by 2 V plus 1 by 2 H nu. So the energy of vibration, the energy of molecule in a particular energy state, V stands for the quantum number. Just like in the rotation spectroscopy, यहाँ पे हमारा था J, so it is here V. So that's vibration quantum number. This is Planck's quantum number. This is frequency of the vibrating molecule with which it vibrates. यानी अगर हम मान के चले, this is a diatomic molecule. So it vibrates to and forth, back and forth. ठीक है ना. तो इसकी एनर्जी हम इसके हिसाब से कैलकुलेट कर लें. ठीक, तो कैसे करेंगे हम कैलकुलेट? मिसाल के तौर पर ना, वी कैन डू इट लाइक दिस. लेट अस सी द एनर्जी ऑफ मॉलिक्यूल. हम ये भी लिख सकते हैं दैट where V is equivalent to, that's vibrational quantum number, starts from 1, 2, 3, 2, 3, 4 and so on. ठीक, so the energy of the molecule is given by, so you can look here, the energy of molecule in the vibration spectroscopy. इसको मैं थोड़ा और अच्छी तरह से बना लेता हूँ. So that is, it can be 1, 2, 3 and so on. Now अगर हम इस हिसाब से देख लें, तो we can calculate the energy for energy level 1, that is equivalent to, इसको energy level 1 means when V is equal to 0 also is here. Energy level 1 means energy level 0, first energy level, that is 0 plus 1 by 2. So the energy will be 1 by 2 H nu. Take. So for energy level 2, that means quantum state 1, V is equal to 1. So you take it 1, it is 3 by 2, 1 by 2. इस तरह से when you go for E2 state, you put the value as 2, 2 to the 4, that's 5 by 2. As you take it E3, then it's 3 to the 6, that is 7 by 2. And in this way you can calculate the energy of a molecule. Now इसका मतलब अगर हम डायग्राम दिखाएंगे एनर्जी की, अब बिफोर विल ड्रा द डायग्राम, अब देखिए जो एनर्जी, दिस इज फर्स्ट लेवल, इसकी स्पीड डिफरेंस क्या है, दैट इज दिस माइनस दिस, सो दैट विल बी इक्वलेंट टू एच न्यू. फाइन. अब इस तरह से इसके बीच में 5/2 minus 3/2, that is the same h nu. This minus that is h nu. That means the energy levels are equally spaced in the vibrational spectroscopy. So हम यहाँ energy level diagram बना लेंगे. यहाँ ये important याद रखनी है कि we are assuming that we are dealing with a simple harmonic oscillator, that the bond length doesn't change. So energy levels are equally spaced. So this is V is equal to 0 state, V is equal to 1 state, 3 state, V is equal to 4 state. तो यानी ऊपर दिस इज द इंक्रीज एनर्जी, यानी इसमें मॉलिक्यूल की एक एनर्जी हो गया वाइब्रेशन, इसमें ज्यादा तेज वाइब्रेट हो रहा है, दिस इज मोर वाइब्रेशन स्टेट, स्ट्रॉन्ग वाइब्रेशन, सो द एनर्जी इज इंक्रीजिंग. तो इसकी एनर्जी हम कैलकुलेट करेंगे तो वी कैन राइट एज पर दिस. इसकी एनर्जी दैट विल बी 1/2 h nu, इसकी एनर्जी दैट विल बी 3/2 h nu, देन 5/2 h nu, देन सो ऑन. यहाँ पे देखा ना कि दे आर इक्वली स्पेस्ड, ये इंपॉर्टेंट है. सो द एनर्जी लेवल्स आर इक्वली स्पेस्ड in the vibrational spectroscopy, and we are talking about the simple harmonic oscillator. It's very important. So we can write energy levels are equally spaced. Energy levels are equally spaced. Remember, this is the criteria when we are dealing with molecule, and we assume that the bond length doesn't change, the bond doesn't get broken down during the course of vibration. So we assume that molecule remains in all these states as a simple harmonic oscillator. It obeys the Hooke's law. ठीक. अब ये होगी एनर्जी ऑफ मॉलिक्यूल, जैसे हमने रोटेशन स्पेक्ट्रोस्कोपी में किया था कि इस फार्मूला को हमने, इट इज इन द जूल्स, रिमेंबर दिस, इसको हमने कन्वर्ट किया इनटू द सेंटीमीटर इनवर्स, बिकॉज एनर्जी उसी स्केल में होती है. सो विल कन्वर्ट दिस energy formula into the centimeter inverse. We'll move to this side. So what we'll do, we'll divide this by, so this energy will divide by hc, that is Planck's constant at velocity of light. So that is v plus 1/2 hc by h nu by hc, so that gets cancelled. So we can write the energy is given by v plus 1/2, and this is nu by c. इस nu by c के लिए हम एक टर्म इस्तेमाल करते हैं, मैं दोबारा will write here. So the energy is given by v plus 1/2 right in the form of omega. So this is the energy of a molecule in the IR spectroscopy, and this unit now is centimeter inverse. तो इस फार्मूला में it was joules, इसमें centimeter inverse. तो अगर आप इस हिसाब से कैलकुलेट करेंगे, दिस गैप इज इक्वल टू omega e omega e omega e. ठीक. So this is the unit conversion. So now we'll talk about this is all about the energy. So the conclusion is that the molecules in the IR spectroscopy, when we see the harmonic oscillator condition, the energy levels are equally spaced. Now we'll talk about the transitions. Molecule absorbs the IR radiations, it undergoes transitions. Now before we start the transitions, now एक important चीज यहाँ पे है, इस फार्मूला में अगर हम v को सब्स्टिट्यूट करते हैं एज 0 इस फार्मूला में, ये बहुत इंपॉर्टेंट है. when v is 0, इसका मतलब the molecule is present in the ground state. जब मॉलिक्यूल ग्राउंड स्टेट में, the energy is given by, अब देखिए v plus 1/2 फार्मूला है हमारे पास, यहाँ पे now we insert this 0, that means energy is given by, that will become 0, it becomes 1/2. इसका मतलब molecule in the ground state has the energy, it has some value of energy, that's 1/2 omega E. और अगर हम इसको in terms of this formula निकालेंगे तो it becomes, इस फार्मूला की कंडीशन में अगर आप इसको निकालोगे it becomes 1/2 h nu. तो आप चाहे इधर you consider this one or you consider this one. That means in the vibration spectroscopy, even molecule is in the ground state, it does possess the energy. इसका मतलब that molecule has the vibration, that every molecule that exists in the universe, even if it's present, wherever it is present, it has some vibration energy, and that vibration energy is 1/2 omega E, or it is 1/2 h nu. So this energy is called as 0-point energy. So we can write the 0-point energy. Energy possessed by the molecule when, vibration energy possessed by the molecule when that's present in the ground state. Like in the vibration spectroscopy, that was 0. When J was 0, energy was 0, but it's not 0 here. So every molecule does possess some vibration energy, even when the molecule is in the ground state. Now, ये बहुत important है. I'll move to the transitions. जिस तरह हमने वाइब्रेशन स्पेक्ट्रोस्कोपी में कहा कि जब मॉलिक्यूल को हम एनर्जी दे देंगे, इट विल मूव फ्रॉम दिस स्टेट टू दिस स्टेट. हमने कहा था रोटेशन स्पेक्ट्रोस्कोपी में, क्या यहाँ पे भी इट विल मूव फ्रॉम 0 state to 1, or can it go to 0 to 2, can it go to 0 to 3? उसके लिए we have the selection rules. Again, the selection rules are derived from the quantum chemistry. Fine. So selection rule इसके लिए ये है, selection rule ये है that delta V should be plus minus 1. That means those transitions which go from 0 to 1, or 1 to 2, or 2 to 3, or 3 to 4, or in case of minus, that is the state, so it's coming from 1 to 0 and so on. They are allowed, so they are intense, and they are called allowed transitions. ठीक. अब vibration spectroscopy में चूंकि energy is higher than rotation spectroscopy, most of the time the molecules will stay in the ground state. So ground state population will be more. So that means the chances of transition from V0 to V1 are more. That means transition chances from V0 to 0 to first state, they are more. So these transition, the chances for this transition are more. Now let us see. Let us see the molecule goes from this state to this state, and it absorbs the IR radiations. So we're talking about transition from V0 to V1. So we can calculate the energy as, so higher minus lower, ठीक, this minus this, ठीक है, this minus this, देखते हैं वो एनर्जी कितनी है. So उसके लिए कितनी एनर्जी में लग रही है, that is V plus 1. अगर हम इस स्टेट को मान लेते हैं V, इसको मानते हैं V plus 1, so V plus 1 plus 1/2, ठीक, minus V plus 1/2, ठीक. So this is the factor. यहाँ हमने V को 1 ऐड किया क्योंकि this is higher state, ये वाला स्टेट, और ये 1 V plus 1, ठीक. इसको जब आप सॉल्व करोगे विल एंड अप विथ दिस टर्म, ठीक. इसका मतलब दिस मच frequency required, this much energy required for making the molecule to undergo transition from V0 to V1. So this is called as fundamental vibration. It's called as fundamental vibrational frequency. Fundamental vibrational frequency in the IR spectroscopy. So the energy which we require, the energy of the this is the energy of the radiation, that should be equivalent to this much. That can make the transition from ground state, that's V0 to V1, ठीक. So that's called as fundamental vibrational frequency, that is equivalent to this much. So ये हो गया, this is the basics of the energy and the transitions which will take place, और जो transition which will follow the selection rule, they will be highly intense, they're called allowed transitions. अब यहाँ last point ये बचता है हमारा कि जिस तरह हमने देखा है rotational spectroscopy में, does all molecules they are active in the rotational spectroscopy. फिर हमने वहाँ rule एक बनाया था that there should be a permanent dipole moment in the gaseous state. Same is the case here, that which molecule will be active in the IR spectroscopy. Number one, the molecule should possess a dipole moment. Dipole moment. That molecule should be polar, like HCl, like NO, like CO, water, and so on. So they have a dipole moment. So they will be active in the IR spectroscopy. Now there is second condition also, that ये भी होता है यहाँ पे कि अगर आपका molecule initially it was non-polar, but during the course of vibration उसमें polarity आ जाती है, ठीक? So that is again active in the IR spectroscopy. So or I can say the molecule, if it possesses a dipole moment and then during the course of vibration, so there is a change in dipole moment, change in dipole moment, change in dipole moment, mu, during the course of vibration, during the course of vibration, course of vibration. इसका मतलब है अगर आपके पास polyatomic molecules है, अगर वो initially है भी, they are not having the poles, but during the course of vibration, क्योंकि polyatomic molecules में options बनती है कि they change their symmetry and they will have some sort of dipole moment, so they will be active in the IR spectroscopy. So we can say that the criteria for a molecule to be active in the IR spectroscopy is that either it should have a permanent dipole moment, or the dipole moment must change during the course of vibration. इसको हम ऐसे भी दिखाते हैं स्पेक्ट्रोस्कोपी टर्म्स में कि जितना ये डिस्टेंस निकालेगा उसके विथ रेस्पेक्ट इफ द चेंज इज नॉट इक्वल टू 0. So this is said to be the criteria for a molecule to be active in IR spectroscopy. All the molecules which are heteroatomic, so and they have the IR, they're active in the IR, and the polyatomic molecules, they also will be active because most chances are more in the polyatomic molecules that they will change their dipole moment during the course of vibration, so they will be active. So homonuclear diatomic molecules will be absolutely not active in the IR, like O2, N2. You can take examples like H2. So they will not be active in the IR spectroscopy. Fine. This is all about the basics and the basics of the IR spectroscopy, the energy of the IR spectroscopy. Again, I'll go here to the slide. So it started the energy of a simple harmonic oscillator, assuming molecules, they are within the limits of simple harmonic oscillator, that means they obey the Hooke's law, and this is the energy in terms of joules. You can convert this into the centimeter inverse, and then if you start calculating the energy, you'll see the energy, all the energy levels, they are equally spaced. Then if you talk about the transition, it follows this selection rule. So since most of the molecules are in the ground state, the ground state population is high, so the transition from V0 to V1 is more. So if you calculate the energy, you will get up this energy. It's called a fundamental vibrational frequency, which you require to make a molecule to transit from V0 to V1. Then those molecules have a permanent dipole moment. They will be active in the IR, and likely during the course of vibration there is change in the dipole moment. They will be active in the IR spectroscopy, and homonuclear diatomic molecules will not be active. So this is all for the day, and then we will next